In this video, we're going to take a look at some sample problems using our knowledge that we just learned about alkanes, alkenes, alkynes. Before you proceed to do the sample problems, you do need to understand the different ways to represent organic molecules in organic chemistry. Those are molecular formulas, Lewis structural diagrams, structural formulas, condensed formulas, and then the carbon skeleton formula or the bond line diagram. So to learn this, I want you to go to this tutorial here. It'll open up a document and there'll be a video within the document. You watch the video, complete the practice problems, and you'll be a pro at representing molecules, organic molecules in different ways. The most common ways that we use are typically the bond line diagram, the condensed formula, and the condensed structural formula. We will sometimes use the structural formula as well. So we're kind of moving away from Lewis structure. In other words, we're not going to put the lone pairs anymore as much because we just care more about the functional groups, for example, but they're still there. So in these structural formulas, we don't typically include the lone pairs, but they are still there because, again, our focus is on functional groups. So please watch this before you proceed, and then return to this video to do some sample problems once you've done so. Here we have a sample problem using the two molecules. Actually, there's three molecules below. Explain the disadvantage of using a molecular formula to identify a molecule. So molecular formula is this over here, just putting the number of atoms and types of atoms that you have. Well, let's take a look at these molecules here. So what I would do if you were approaching this problem here, and hopefully you tried it first and then you unpause to check your work, is try to find the molecular formula of each one of these and see how they compare. And then that might lead you to some ideas to how to answer this question. So if you actually count everything, it looks here like I have how many carbons? 1, 2, 3. So 1, 2, 3, 4, 5 carbons. And how many H's? Well, 1, 2, 3. Then 3 here, that's 6. And 3 here, that's 9. 10, 11, 12 H's. 12 H's. Okay, for pentane, I have C5H. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. C5H12. So 2-dimethylpropane, C5H12. Pentane, C5H12. All right, let's try 2-methylbutane now. 2-methylbutane. Looks like I have 1, 2, 3, 4, 5 carbon, one in the branch there. So I have C5. And then for my hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. H12. Interesting. So you can see that these three different molecules have the same molecular formula. So many molecules have the same molecular formula. The molecular formula only provides information about the makeup or composition in terms of atoms, the atomic makeup, but nothing much about structure. So really, I don't, if you tell me C5H12, I don't know what you mean. Do you mean this? Do you mean this? Do you mean this? Are there more? So it's not very specific. It's very broad, it's not as specific as it could be. So if in organic chemistry, when I want to talk about a specific molecule, yeah, I might maybe start off by mentioning its molecular formula, but I do want to give you some more details about it. So I probably want to use any one of these other representations here to give you a better idea as to what the molecule actually is. So it can't tell you what the molecule actually is. Here, determine the molecular formula for the following hydrocarbons. When writing a molecular formula, the order is CHON halogen. So, don't put H first, put C first. So this is the general order you'd follow. Classify the following hydrocarbons as either aliphatic or aromatics. So let's start off with the classification first. As aliphatic or aromatic. And then we're going to go, if we're aliphatic, then we're going to try to say if they're alkenes, alkynes, or alkanes. So if I see a benzene ring, then I know it was aromatic. If I don't see a benzene ring, which I don't see in any of the other ones, then I know these are aliphatic. Okay. So these here, and this is not a benzene ring because there's no alternating double bonds here. So aliphatic. So I'm just going to say Al or aliphatic, also aliphatic, and then aliphatic. So now I'm going to go and try to classify the aliphatic ones as either alkanes, alkenes, or alkynes. So remember the alkenes have CC double bond, and the alkynes have CC triple bond. And the alkanes only CC single bonds. So here I have a double bond, so that means I'm dealing with an alkene. Here I have only single bonds, so alkane. Here I have a triple bond, so alkyne. Here it's only single bonds, so it looks like an alkane, but it's a ring structure, so I'm going to call it a cycloalkane. Here again, only single bonds all around. There's no double bonds there. So, and so that means it's an alkane, but it's a ring structure again. So I'll call it a cycloalkane. Here I have the double bond, so that's an alkene, but it's a ring, so cycloalkene. Here, well, you know, it's just aromatic, it's just benzene. Here we have a double bond, so that's an alkene for a double bond. Let's take a look at the formulas. The formulas you can do by just counting, or you can remember the general formula rule we saw. So remember alkenes, their general formula is CnH2n. So let's test it out. Here I have how many N is the number of carbons. So 1, 2, 3, 4. So C4H, if it's really an alkene, it should be 2N. 2 times 4 is 8. Let's see if that's right. 1, 2, 3, 4, 5, 6, 7, 8. C4H8. Alkanes, remember their molecular formula was CnH2n plus 2. So we have 2 carbons, H2n plus 2. So 2 times 2 is 4, plus 2 is 6. Let's see. 1, 2, 3, 4, 5, 6. That worked out. Alkyne. Alkyne was CnH2n minus 2. So we have 1, 2, 3, 4, 5, 6, C6H. So 2N is 12 minus 2, 10. See if that's true. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C6H10. Okay. This here is a cycloalkane. Cycloalkane has, let's see, that's CnH2n. Instead of 2n plus 2, because it's a ring, you have to remove 2 hydrogens to make the ring. So that would be the general formula for cycloalkane. You could also just count, but let's see if this is true. So we have 1, 2, 3, 4, 5, 6 carbons. And then if it's a cycloalkane, it should have 12 hydrogens because that's 2n. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That works. Now, this one here is a bit trickier. So you'll notice that it's a ring structure and it's an alkane, a cycloalkane. And if you just counted these as carbons, you wouldn't know how many hydrogens there are. The hydrogens are not drawn in when it comes to the bond line diagram, as you learned in the tutorial. So remember, carbon can have a maximum of 4 lines connected to it. And so if you don't see any double bonds or triple bonds, then the lines that are connected to it must be other carbons and H's. So this carbon over here has 2 lines from here and here, and the other 2 must be from H's. So that's H, 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 H. So you can see this molecule is actually the same as this one, just drawn in the bond line diagram instead of in the format that you'd see over here, the structural formula. So this was a structural formula, and this is a bond line diagram. So it's the same formula, C6H12. They're actually the same molecule. Okay, let's take a look over here at the cycloalkene. So the cycloalkene, you can use the general formula, but we can also go in and just see like where the H's are and count those. So remember that each carbon has to have 4 lines connected to it. If you don't see 4 lines and the other lines are not shown, must be hydrogen lines. So for example, here we have H, 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 H to make 4 lines on the carbon. H, 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 H. This one has, so 1, 2, 3, 1 H on it. And this one has 1, 2, 3, 4. No H's on that one. And this one simply has 3 H's. So we have C, okay, 1, 2, 3, 4, 5, 6 C's, 7 C's. This is a C2. C7, H. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I think that makes sense because the cycloalkene, if you remember the general formula, was CnH2n minus 2 because it's a ring. A regular alkene is CnH2n, but as soon as you make it a ring, you take away 2 more hydrogens. So let's take a look at this aromatic one. The aromatic one, this would have the benzene ring, but it's not just benzene, so it's not C6H6. You'll notice that we have a carbon connected to it. So there was a general formula for that, CnH2n minus 6. But let's just go count to see if that makes sense first. So remember, each carbon has 4 things connected to it. This carbon's fine. It has 3 H's plus this here. So this one has 1, 2, 3. So there must be an H there. Must be an H there. No H here because there's already 4, right? 1, 2, 3, 4. This one here has an H, an H, an H. So we have 7 C's, C7H. Okay, 1, 2, 3, 4. Just make sure there's an H there. Let's make that a bit more clear. 4, 5, 6, 7, 8. C7H8. And I think that makes sense because the formula was, if we write that out here, it was CnH2n minus 6. So it would be C7H, so 2n is 14, minus 6 is 8. Or you can just draw out the hydrogens and count them from there, and that works as well. So what I would do is practice doing both. Practice using a general formula, and practice counting. Notice that minus 2 makes sense because you lose 2 for every double bond you have, 2 hydrogens for every double bond you have. So we have 2, 2, and 2 taken off there for each double bond there. So that's 6. And then when we had one double bond, well, we had CnH2n, which makes sense because compared to the alkane with no double bonds, it's 2n plus 2. So 2n plus 2 minus 2 is CnH2n. And then for the alkyne, well, it's CnH2n minus 2, which is minus 2 from the 2n. So that's because we added another line in there. So for every line you add, you are removing the H's. And ring structures too remove H's, right? Because you have to connect the ends and remove H's to do that. So here's an alkene now. Alkene, remember we have CnH2n. And so that's going to be, let's see how many carbons we have. We have 1, 2, 3, 4, 5 carbons. So C5H10 is what that should be. Let's just check to make sure that's true. So each carbon has to have 4 things bond to it. If you don't see something bond to it, it must be H's. So this carbon here has the 1 carbon over here, so that's 1. So it must have 3 H's connected to it. This one here has this and that. That's 2 things, so it must have 2 H's bonded to it. This one here is 1, 2, 3, so it must have 1 H to it. This one here has 1, 2, 3, so 1H as well. This one here is just one thing connected to it, so it must have three H's. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. C5H10. So there we practiced drawing H's into bond line diagrams using general formulas in order to solve some problems and find the molecular formulas of a variety of different organic molecules that were either aliphatic or aromatics. So now we're going to finish off this problem-solving session by trying to write molecular formulas for a variety of hydrocarbons that fit certain parameters. One parameter is that it has to contain 10 carbons. So we want to draw an alkane that contains 10 carbons. We know alkanes are CnH2n plus 2. So if we want 10 carbons, that would mean we have C10, because N is 10, number of carbons, H. So 2N is 2 times 10, which is 20, plus 2, C10H22. Alkenes, that is CnH2n. So our alkene with 10 carbons would be C10H2n, so H2 times 10, 20. Alkynes, CnH2n minus 2. So that would be C10H. So 2n is 20 minus 2, 18. Cycloalkane, that's almost like an alkane, but it's a ring structure instead. So the ring structure would have 2 carbons less than the chain structure, than the straight chain, because its general formula is CnH2n, almost like an alkene, but there's no double bond. The reason you lose H's is because you have to connect the ends of the molecule to make a ring, and you have to make room for that because carbon can only take a maximum of 4 hydrogens. So we have C10H20. And that would be our cycloalkane with 10 hydrocarbons. And I could ask you this for any number of hydrocarbons. Any number of carbons in a hydrocarbon, you just need to make sure you can use the general formula to come up with a formula for it. Now, keep in mind, this is not specific. This could be a whole host of hydrocarbons with different number of branches. So some C's taken off the ends, put in the middle. Either way, they'll all fit the parameter. The point is that you can recognize that this is going to be an alkane because of the general formula that we know.